Is the recording on? Yeah, the recording on. Okay, let's start. I just want to make sure the recording is going on. Testing, testing. Okay, it's all going on. Okay, good. Okay, yes, not yesterday, last week, we talked about the sorting algorithm, which is a very typical way of explaining how do we do algorithm in different ways. That can be faster or slower. Thanks, Dr. Hush. Yeah. And today we are more formally talk about order of growth. I will say it's a very good indicator that, because I know that some people may have the mind they want to change to computing. Yeah, but I don't know what is your reason. Some people just think that computing because they can make money, but some people think that they are actually really interested in computing. Of course, I know that not everybody are interested in computing. So today, what we talk about is more on the side of computing. That means if you are really go into minor or major in computing, this will be your life. But on the other hand, order of growth is actually a very good computational thinking method for your life. It's not only for coding. In your future, probably you do engineering, you have to create some process. Maybe it's even a chemical process. Maybe it's even it's an HR process, a human process that you want to think of what will be a good way of implementing it. Why is it fast? Why is it slow? And you have a way to talk with it. We call it the order of growth. Okay? You know that in physics, the whatever string theory, whatever talk about time and space. And you know, Einstein and even Newton talk about how this time and space actually related. They said that if you travel fast enough, your space will be contracted, your time will be longer, whatsoever. Okay. However, in computer science, we also talk about that. So in computer science, we actually do very, very serious about what is the time for your computing, the algorithms, the time you need, in which that means we are always improving on the speed of computing something. On the other hand, space is also an issue, meaning that the space is how much memory you use. Sometimes it's not about memory only. Sometimes it's about the disk space or the temporary space. How do you use? And sometimes the space is even about remote space, because some of the computing is remote. You need to go to the network across, get it, how much network space, network speed you need to do. So we do want to consider that. However, we are not measuring accurate time. Let's see. I don't know what is a long series now. I know the unending story series is like Avengers. Let's say today you want to have the movie, okay? I know now we do Netflix, okay? A lot of people just go and stream it. But if you want it to be on your computer, that means you have a sense of owning it. Will you prefer downloading the movie, or will you prefer a 2-day shipping for the DVD? Okay, but let's don't talk about your preference, what you like, because some people really like the object of the DVD. They want to line them up on the shelf so they can see, I'm a collector, okay? Some people actually, hey, my home is very small. I only want to, let's don't talk about that. I just want to talk about you can have all the data in your home. You can get it out to watch it anytime you want. If you want to talk about the speed of acquiring it, which one is better? The one, right? Probably downloading the whole movie of the whole Avenger, even is Blu-ray quality, it won't take you more than half an hour. So you can get the whole file in your computer. Yeah, in this time, downloading is faster. How about I want more? I want the whole saga. The whole saga, I think it's not only 23 or whatever, maybe go up to 30. I want all the movies. Which one is faster? Well, you think that 23 movies, maybe each of them is half an hour, you still need 12 hours to download, maybe at most 1 day, 24 hours, right? So the 2 days prime shipping maybe still slower. So if you just want to talk about the speed, I will still prefer downloading. But what if you want more? I want whatever anime you want. You want Pikachu, whatever, Pokemon, or any movie you want. I also want Harry Potter series. I also want my Lord of the Rings series. I also want my whatever, Wednesday, whatever, okay? Making advertisement now. I want them all in my home. If you increase the number of movies you want, which one is faster? Which one you get it faster? So you will notice that downloading a movie in the first place is faster. Probably if you download less than 50 movies, it will be faster. But if you want to compare to shipping, what is the shipping curve look like? The shipping curve will look like this, right? No matter how many movies, of course you're not mentioned, but even if you order 1,000 movie, maybe they get a truck to go to your home, is still 2 days. So what I try to say is here, sometimes, yeah, when we're doing on daily life basis, when we want to, I want to do Grab food, right? It doesn't matter so much, is it I go order Grab food or I go to the real place to buy it. But if you talk about your task is depending on a large volume, it may change someday that certain method is faster. So in this diagram, the delivery may be 2 days in the beginning, but after certain time, thank you. After certain time, your download rate will be forever slower. My point is forever slower, right? After the point of intersection, your downloading time is forever slower. So a lot of algorithm can be considered this way. So you can see the 3 stage. The first is the transient stage. It's hard to tell, right? So either I grab food or I actually order McDonald's, it doesn't matter. But after a certain point of time, some method will surely win. That's what we want to talk about. And the next idea is we want to talk about in the large scale. So the ultimate question in computer science is, if the volume keep increasing, you're going to process a lot of data, because the point is, if you want to just process very small data, you don't need computers. You may just need calculator or man to calculate it manually. But if you want the volume increase, millions items of data, a trillion number of data, you want a computer, you want to find a way that is a lot faster. But that will also be in terms of time and space. So let's see in our computer science point of view. Now I want to say that you want to compute factorial, and I want to compute factorial 10, factorial 20, factorial 100, factorial 10,000. Compare with Fibonacci number. I want to compare Fibonacci 10, Fibonacci and whatever. Do you think they will compute in the same order of growth? And how do you tell? The question is, how do you tell? How do you use a language to model it? I think use the language or mathematical formula to model it is one of the biggest invention in humans. Otherwise, if today you think that, oh, when you go to the marketplace, I want to buy some pork or meat or vegetables, you don't have the language. How many grams or how many pounds? And I don't know how much money I need to pay you. $10. There's no way of describing it. How are you going to do the trading, right? So inventing a language, how do you describe it, is the most important thing. Let's see first. First of all, I will not going to measure the absolute time. Why? Because you may measure the absolute time in different computers. It can be on your grandma, very slow computer. It can be in your state of art, whatever the country's supercomputer. Some can be faster, some can be slower. We are not measuring that because that won't change your algorithms. Which we want to say is, what is the proportion of growth when your data input is larger? So if you talk about last lecture about sorting, we'll compare when you sort 10 items, 100 items, and 1 million item, how do we distinguish that instead of which computer we're using? So I try to do a little experiment on this factorial and Fibonacci. And you know that we can implement both in recursion way, okay? So what we do is, this is the old code, you understand? I do a little thing to do what we call profiling. Profiling means I want to actually know how many times they call your recursive function. So what I did is this. The red lines are not functional. It doesn't affect the output of the two functions. But what I did is, it's like a counting, okay? I count how many times the function is being called. And I do this statistic. So nFact and nFib are the number of times they call the function. And each time when I enter the function, I increase the number by 1. And if you understand the local and global variable, you know that I cannot simply say nFact increased by 1 because it will be treated as a local variable. I will refer to a global variable as the profiling. Let's see. First, the first competitor is factorial. Now let's try to compute factorial 5. And now the number of calling of the function is 5 times. It makes sense, right? Because each time you call the function, you reduce the n by 1. So if you're computing factorial 5, you call yourself 5 times. So let me reset the number of counting to 0. I try to compute factorial 10. So what do you expect? How many times do you call? 10 times, right? Because I call myself 10 times, each time I reduce n. If you want to compute factorial 20, I call myself 20 times. This is simple, right? Let's consider the Fibonacci. So if I want to call Fibonacci 5, I need to call myself 15 times. If I want to reset it, I try to compute Fibonacci 10. I need to call myself 177 times. If I want to compute Fibonacci 20, oh dear, I need to call myself 21K times. Why? And do you see the order of growth? The order of growth of factorial is actually proportional to the number. But what about the Fibonacci? So if you go into that, you can compare. The growing is not in the same way. We call it is not in the same order. Factorial is very simple because we know that each time I call the function n, each time I call myself again, I will reduce by 1. So if I call function n, then very simple, n times. Maybe it's n plus 1 time, maybe it's n minus 1 time, maybe n plus 2, n minus 2, but it doesn't matter. Because if n grows, the number of calling with the factorial is linear proportional to your number you called. That's why we call this type of algorithm is the algorithm that is proportional to your n that is input. Linear proportional. Fibonacci is more complicated. How do we visualize its computation? It's a tree recursion. What does that mean? How do you compute Fibonacci 5? You have to call Fibonacci 4 and Fibonacci 3. Then the next question is, how do you compute Fibonacci 4? Fibonacci 4 have to compute Fibonacci 3 and Fibonacci 2. Then go on. If you want to compute Fibonacci 3, you need to compute Fibonacci 2 and 1 and so on, blah, 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 blah. And all of this, you have to compute until you reach Fibonacci 1 or 0. Then you don't have to go further into the recursion. However, you forgot that on the other side, you still have to compute Fibonacci 2. And then on this side, you still have to compute Fibonacci 3. and so on. So that means if you treat this diagram as a shopping mall, and each of the items is a shop, you have to go through every shop to compute Fibonacci 5. Then you can imagine if I want to compute Fibonacci 10, the tree is very big. Well, how big? What is the number of node, we call it, number of computation I need related to n? This is the root, and I need to compute until all the leaves. Roughly is half of a full tree. Full tree means every time I double until the rest. But then how many? Very simple. The first level is 1 node, right? The second level is 2 nodes. The third level is 8 nodes. Each time you double. What is the number of nodes after you go to the last one? You double how many times? If it's n, you double n times. So it's 2 to the power n. That means according to your n, you have to compute items that need 2 to the power n times. But you say it's not a full tree. There's a lot of space here. You don't need to compute. Wait a minute. Am I recording? Yes. Wow, scare me. So, but how come I don't have the pen? Hey, where's the pen? Yeah. But you say, wait a minute, it's not a full tree because you see, this side of the tree is not completed. Okay, I'll give you that. It's half of the full tree. That means it's 2 to the power n divided by 2. Then it's what? 2 to the power n minus 1. Is it good? It's still not good. Even divided by 2 is not good. So that's why we will actually grab this, we call it the polynomial or the formulas, to actually measure how our number of computation increases with the input. So if you see that, I don't know why this one always like that. They always cover my last line. So you can see that the factorial, we can conclude that the number of times you called is proportional to n. And then for the Fibonacci, the number of core is proportional to 2 to the power n. And let's go back to some of the algorithm we learned last time. How about linear search? How many times I need to compute? We say it doesn't call recursion, but then we count how many comparison. Comparison means how many times I need to check an item is with me. But you also say very fast, if the first item is my item. But I'm sorry to tell you that usually computer scientists are pessimists. That means they want to talk about what is the worst case. Okay, so they need to know what is the worst case you can do. So if you do linear search, what is the worst case? The worst case is what? ON. But why is it ON? Because the worst case is you try to search for the whole list, you have to go through every item. For example, if your item is not in the list, you have to go through everything. So that means the number of comparison you need to search in the list is proportional to n. That's the worst case. You can also analyze its average case. What's the average case? That means by average. Sometimes it's on the left, sometimes on the right. So what is it by average? Then you need to some probability, okay, just to let the cat out. What is the expected number of search if, let's say, your item will be equally chance on every part of the array? Probability. I just let you have it. If you just calculate probability, if you have n items, the number of search is n over 2. It's very simple. For example, if you want to roll a dice, what is the expected value? It's 3.5 because it's adding everything and average. Okay, so if you want to calculate what's the average, is I will have 1 times, I have 2 times, or 3 times, or add all of them and divided by n. So it's n over 2 in average. How about binary search? It's proportional to log n. Because every time you have it, by calculation, the number of times you need to narrow down to your search is only log n times, because we divide the list into half every time. How about the insertion sort or bubble sort? Insertion sort or selection sort we talk about, remember that the sorting algorithm, we have to select the smallest. But it's very fast, n times, right? Every time I get the smallest to the rest. But wait a minute, how do you find the smallest? Finding the smallest need you to check everybody. So to find the smallest for n items, you need n steps. To find the smallest for the n minus items, you need n minus 1 step, and so on. All together, how many times you check is 1 plus 2 plus 3 plus 4 all the way to n. And that's why all this sorting algorithm is n squared. Because you say not n squared, it's n times n minus 1 divided by 2. But we usually do this order of rows is depending on the highest degree of the polynomial, which is we also neglect the coefficient. But how about merge sort? This one wait until you go to 2040 lah. Merge sort is n log n, which is the best sorting algorithms comparison sort complexity. Okay, so maybe you say, oh, I don't care. Okay, I don't know how to do the math. My math is bad. Well, we can do experiment. What we do is we really run the sorting. So if this code, you don't really have to understand it. So what I do is I do ln is the list of the number of items. I randomly generate some item and do sorting. Okay, so the whole thing, the time package is just to import a time. I just do a timestamp. What I did it here is I do a timestamp. I record what was the time before I do sorting, and then I record what was the time after sorting, okay? Time function is the function that get the current time. The way you get the current time is how many seconds has passed since a date. I think it's 1960, whatever. You get the number of seconds. But then when you get the timestamp at beginning, the timestamp at the end, the difference is how much time you use during the function. And we do it for bubble sort, and we also do it for merge sort here. And then, ta-da, there's a graph. And you can see that the bubble sort is really a curve that is quadratic. Okay, the orange line should be something like almost linear, but I think because the quadratic line is running too fast, so that's why it's hard to see. And all of these will be in your 2040 core algorithms. Anyone can give some algorithms. For example, I think we mentioned about it before. It's called Bogle sort. How do you do sorting? I don't care. I randomize everything. You give me an array, I do a random permutation. I shuffle it. And then I check if it's sorted. Remember last time the story? I sort your paper, I throw it in the air, get the thing back and see it's sorted. If not, I throw them in the air again. How much time do I need to sort this? This one is, if you wait long enough, L is sorted. Okay, but then how long is it? Anyone heard of the theorem called Thousand Monkey Theorem? You can search for it. It's a scientific theorem or theory, I don't know, or law. They said that if you give you as many monkeys as you want and give them as many typewriter as they want, if you give them long enough time, one of the monkey can type out randomly the whole Shakespeare collection. You can search for that theorem, okay? And I think that's people, how do they rely that on evolution theory? Because you are also like random typing and you come out for your DNA, okay? That will come out. But of course, you have some evolution criteria, selection, and so on. But that was what the sorting is waiting for. However, anyone can give any algorithm, but how fast is it? How do you talk about that? For Bogle sort is n factorial, but if you are on a different computer architecture, if you can actually do quantum computing, you can be fast because you can destroy the universe. Okay, so you can actually create parallel universe to compute the different bits in the same time. Then you can actually compute faster. Come back to us first. We don't have a quantum computer. Okay, I don't know when will be the time in human race everyone has a quantum computer on their watch. Maybe the one time will be like that. Okay, but let's talk about back to reality. Okay, now we don't have a quantum computer. How do we improve our Fibonacci computation? One very easy way you know that. Why is this so slow? Because you do some silly things. You recompute a lot of things. For example, here, you see, I compute Fibonacci 3 here. I have to compute it somewhere else. I recompute it again and again and again. I recompute Fibonacci 3. If my number is larger, I need to recompute a lot of Fibonacci number again and again. So what is the clever way of doing it? I memorize it. How? This is called memoization. Okay, these are techniques. Actually, Python have a decorator for that. That means what I do is the real code is the same as Fibonacci number. However, here, I create a dictionary for the answer. That means before I really be good and very diligent to compute the answer first, I check if I've done it before. If I already can find the answers in the saved dictionary, why don't I just go and get it from the dictionary? Okay. So if it's like that, I directly return the answer stored in the dictionary. However, if it's not, okay, I go and compute it by recursion. But before I return my answer by my very diligent effort, I will save that answer in my dictionary. So if somebody need to call that again, okay then I give you okay? I give it from the dictionary instead of I recomputing it. So the dictionary serves as like a cache. So you remember all the answer you had before and you don't have to recompute it. And then the question is, how fast is it? Then become ON. Because why? Every Fibonacci from 1 to n, you only have to compute once. You only have to compute once. Otherwise, you don't have to recompute it because you remember it. Okay? That's faster. But why is it not so good? The not so good thing is because you have to remember all the numbers. Okay? Let's see how do we do it faster. I also don't want recursion because you know recursion can limit your recursion step. I cannot compute Fibonacci 1000. So instead of that, actually I can use an array. What does that mean? I use a list. The list is I actually store all the Fibonacci number 1, 2, 3, 4, 5 in array according to the index. So in index 0 is Fibonacci 0. Index 1 is Fibonacci 1. Index 2 is Fibonacci 2 and so on. But then how do I compute Fibonacci 3 now? I get the answer index from the previous before, and after I compute it, I append it to the list. So after this, I will have the whole list of Fibonacci number from 0 to n. Then I just return the last number is my Fibonacci number. Okay? But still not good. Why? If I want to compute Fibonacci 1 million, I need to create an array of 1 million item long. And why is it not good? Actually, if you want to compute Fibonacci 1 million, do you need the number Fibonacci 0 to Fibonacci 99999? I don't care. I just need the last number. But if you want to compute the last number, you need the previous two number. How? Okay being cheaper, I just remember the previous two. Because every time Fibonacci, you need to remember the previous two. So I only keep track of the previous two numbers. So this is the last Fibonacci version. So what happened is, if Fibonacci is 1 and 2, I will return 1. Otherwise, I know that the previous two number is 1, 1, starting from 3. And whenever I go, I would compute the new Fibonacci 2 is the sum of the last two Fibonacci number. And Fibonacci number minus 1 is the last two Fibonacci number sum here. So this is the last number. The last number is the sum of the last two Fibonacci number. And the last two numbers is the last Fibonacci number. So I move the window of computation all the way. Why is this good? Because no matter how large your n is, I only need to remember two numbers. I don't have to remember so many numbers, okay? So this one, why is it better than the previous example is, this Fibonacci version has the same time complexity as before, which is O(n). But this win in the sense that this Fibonacci number use less memory. So the previous Fibonacci number, its bit is O(n), but its space is also O(n). But this Fibonacci number, speed is O(n), and the space 1, because no matter how, you still remember two numbers only. So that is how this lastly win. But is it the best Fibonacci number you can do? Actually, it's not. In CS1010E here, I want you to know how to compute Fibonacci in O(n) time is good enough. The faster algorithm can be log(n) because you can use something called matrix algorithms. Actually, if your Fibonacci number is very small, there's even an explicit calculation. But I don't buy on that. Those are very heuristic method. Okay, you can actually compute a small Fibonacci number by a formula, but that's not accurate for bigger Fibonacci number. So if you really want to improve this, continue, okay? One is 1231. 1231 is more on discrete math. Too bad that math is actually based on a lot of our engineering and computer science. I know that most of you may not be so happy about our math education in our high school or secondary school, but actually there is really a base for everything. 2400 and 3230 in CS are totally on that. We'll drill on that. We'll go into that. What are the different sorting algorithms? How do you compute the shortest path? Which means if you come from NUS to go to Changi Airport, what is the best way to go? Okay, they actually can compute the route, how much it costs, how do you minimize most of your resources to do something, or how do you schedule your study plan, or how do you do a lot of computation? That is useful for most of your engineering, even projects or algorithms, okay? So that is our first part of our lecture. Yeah, there's a big O notation. We'll have a small break and we go to talk about exceptions. Exceptions is one very useful Python, so-called Python features. Yeah, so we'll pause a bit and we go on. Know what I answered. Okay, let's continue. Exceptions. No, I cannot do this. Errors are an exception. You already got a lot, right? You already got a lot of errors. What are the types of errors? I think we divide it into two main types. But first of all, we talk about what are errors. We didn't talk about the debugging. Do you know that a lot of computational error actually contribute to a lot of loss? Let's don't talk about the tragedy, this recent, like the airplane crash, whatever. There was once upon a time, I think it's NASA, they try to shoot a rocket or space shuttle and they explode. Lost a lot of money. It's like a few $100,000 million. And then they find out it's because in their code, they misspell an underscore as a hyphen. That makes the code fail and the whole spaceship explode because of that. So errors are quite, you see that how important it is because some of the systems are life critical, like our MRT or nuclear plants or airport management system. Some are not that crucial. So in our computer science, there was one course called real-time critical system that you need to do a lot of things to prevent errors. And we need to handle errors, okay? But however, for our level, there's another level of error called syntax error. So syntax error is like that when you forgot to do something. For example, this one, what you forgot? You forgot to put a colon there, okay? So we don't actually talk about that because syntax error usually will be being taken care of when you're doing the coding. Okay, so we don't really care about so much about syntax error now today because you should be able to handle them. What we talk about is exceptions. That means the compiler accepts your syntax, but when you run the program, you got it wrong. Okay, so syntax error compared to English, I would say syntax error is something like grammatical mistake. If I say he don't want, this is a syntactical mistake. So for syntax error, you can check it by your Microsoft Word or whatever, they can check it out. But exceptions and runtime errors are like runtime errors are like some logical mistake. Okay, so for example, if I say what is a logical mistake? I'm a lecturer and I'm earning $3 trillion per day. Grammatically, it's totally correct, but it's a logical mistake because I can't. Okay, or the sun is rising from the west. That is totally correct grammatically, but also logically correct. Sorry, logically incorrect. Okay, so we'll have that. When you have those, you may have it, your program crash. Like this, this is called zero division error. That means the syntax is okay. Totally syntax can pass, but when you compute it, Python cannot. What is 1 divided by 0? No one knows, okay? Mathematician may define it out, but when you do Python computing, you cannot compute 1 divided by 0. At this point, Python will crash and tell you these red words. And you can see at the last line of the red word actually tell you there's something called zero division error. And actually in Python, it called it exceptions. All these error messages are exceptions. This is one of the type. And it's like other exceptions, like name error. That means the spam variable is actually never defined. Or type error, you try to add a string to an integer. So all this error, Python will crash your code, stop it totally, and then throw you these red words to tell you what goes wrong. Like this one is a value error. Integer can take in a string, but too bad your string is not able to convert into any integer. I say one is not a number, not a digit. Integer function can only take a string of digits to convert into integers. Okay. So the question is, how do we handle errors? If error occurs, what do we do? First of all, how do we detect them? You can use a lot of if then else or totally lie down the logic. But in Python, there was one, actually not only in Python, in quite a lot of language, we have this thing called exception handling. That means I can do this try block. Try, I add a try there. So maybe let me demonstrate through some real coding. So usually the concept is like that. Okay, I can do some code. Maybe I want to compute I want to write a program about a calculator. Okay, I want to do I want to write a program about if I have some money, how do we divide for different people? So I do that. Total money is equal to input. How much do you have? Okay, and number of people, n is equal to how many people Do you want to divide the money? Okay. Okay, very simple, right? Then I print. Each person will get total divided by n dollars. Okay. Oh, no. Let's just make it simple. Okay. Then for normal programming, I would say, how much do I have? Let's say I have $1,000. And then how many people do I have? I have 5 people. Okay. And everybody got 200. Okay, right? I can run the code again and so on. Run it again. I can have $10 and divided by 20 people, and each body have 50 cents. However, what happened if I do this? I have 1,000 number, but I have 0 people. Okay? But then you say, oh, actually I can write if then else, right? I can write if then else to check, oh, if the number of people is 0, whatever, then I tell whatever. But that was a better way to do that, which is here, I do a try block, except maybe I've been error, not, cannot do it. Okay, what it does is originally you have some code, but then you put it in a try block, and if any error, you go to except. So if the good thing about this is if you just do normal computation, let's say if I do 80 divided by 8, normal computation, it doesn't affect the flow. But if you do something naughty, like here, 100 divided by 0, the program won't crash now, but will execute your code, and even you can continue your program. Okay? You can even say, let's go home. Okay? So if you have $99 divided by 9 people, okay, let's go home. But if I have $1 divided by 0 people here, go on, okay, let's go home. So you don't want to interrupt your program. Why? Imagine that there's one time you put a phone, right? You do some operation, maybe you are going PayLah. In PayLah, you try to type the money you want to transfer and pay, and suddenly you pay 10, you pay 10, and then it crash. You won't be happy. If you are filling some form, you know, sometimes you have to nasty like fill in the immigration form, whatever, right? You fill in, after 10 minutes of filling in, the program crash. You are not going to be happy with that. Okay, so you must not just crash the program in order for illegal operation. So what it does here is we can actually use this try block to catch the error. That means you can actually totally prepare for the error. For example, here, I can do except 0 division error. That means if your error is actually 0 division error, you actually can know. Okay? So the try cross means the try block is being executed. If there's any errors or exception occurred, they will go to try to find, and it's like emergency exit. You kind of find, for example, in this building, we have emergency exit for the fire or whatever. But however, if it's safe phase, like every time we do a lecture without earthquake, then the except cause will be ignored. So you don't need, for example, it's like our fire extinguisher, right? If there's fire, you go for that. But no one wants to go for that if nothing happened. So interestingly, there's something called finally. Finally will execute no matter what, no matter no error, no matter you have exception handle, no matter even you crash a machine. Okay, so the try, but you can have more than one except. That means you can actually get ready for more than one type of errors, but only that one handler will be executed. It's a bit like if then else. That's why a lot of people abuse it for if then else. Let's see. For example, let's have a high-level thought first. On the left is some types of simplified program. I try some statements, and there's a few errors I expect. Error 1, error 2. And if you don't put anything in that, for example, this one error 2, you specify is some error 2, but you can actually do this, which is a wildcard. Any error I didn't expect, go there. And also it has an else, which is kind of redundant. I think in my 40 years of programming, I never do this. That means if no error, I do that. Finally, there's a finally. We'll explain what is a finally later. So let's try. If let's say today I run a code, that is actually no error, we'll go through this. I will execute all the statement here. If no error, I will skip all the except, and then I will actually execute the else and finally, and I continue with my program. This is what happened if you have no errors. However, if in the try block, the statements there, you have some error, then you go to the exception handling. You will find the corresponding errors. And then you handle the error and go to the finally, and your program will continue. Or maybe it's another error and so on, okay? So the error, the exception handling is something like emergency exit. Maybe we have a more better example to do that. This is a concrete example. For example, this one is called, I try to write a function called, I try to divide x by y. And in here, I actually have some error I expected, okay? I expected 0 division error. I expected, actually, maybe I better write the code and run it. Okay, so I test out the code here. This is my code. So what I did is, x is equal to input, y is equal to another input. I try to do divide x, y, okay? Actually, I can, no, not x, y. I directly do that, don't do input. Divide x. So if I do divide x 10, 2, they'll be okay, right? Because it's just x divided by that. And then I run it. Let's take a code. I execute the try block. And then because I don't have any errors, so I don't do this. And then I will finish the else. And finally, that's why I print the result is 5. Execute finally cross. Okay? I can have more error expected. For example, I accept type error. Okay. Here I print the type is not right. Okay. So I can have more except blocks. I can even have an except that some error is found. So now if I do this, I can ignore all the except. But what if I do this? 10 divided by 0. Then when you execute this cross, you got wrong. But you try to find some way out. And you have the choices 0 division error, type error, and any wildcard. So if I run this, you see, I find that it's division by 0. Okay. So what if I do some crazy thing like I want to say 70 divided by 7? I have a string divided by that. Then I will find the error is the type error because the type is not right. Okay. However, what if I want to find some error that is not in the list? For example, here, if I don't have the division by error, if I want to divide 70 by 0, what happens now? I will try to find if there's any type I match. But however, no, I got a wildcard. That's why if I run this, yeah, some error is found, but I don't know which one because I didn't cater for it. Okay, but what if I even don't have the wildcard? If I run this, but you say error handle that I already prepared. I still got the error because I didn't have any except to handle the error. But one thing interesting, do you see what is executed? Finally. So that means this finally cross here, no matter what, no matter you execute the program without any problem, no matter you execute the program with some error you handled, or you actually execute the program, even you crash the program and stopped, the finally will be executed. Okay, what does that remind you? Do you ever watch those China movies or any movie? Always have this scenario when the boyfriend almost die, right? On your arms, what would that do? Usually before some people die, they'll tell you something. Oh, actually, I love you. Actually, the son does not belong to you. Actually, what? I mean, they tell you something, right? Then they, very interesting. They will tell you something and then they die. Okay? That is for that. Finally is for that. Why is it important? Finally is the last safeguard object can for two purposes. One is for emergency. If you are programming something like seriously, you're programming the nuclear plant, okay, and some error occurs, you better prepare for everyone. But what if really something you didn't prepare for? Maybe the finally cross is finally let's shut down everything, or finally let's do something desperate. Let's just blow up the whole plant, whatever. So finally is the one you want to do it before your program totally lost control. Or the other purpose usually we do it is, anyone knows what I call them? Call them. That is for Unix system or for other system. A lot of times when your program runs like Unix, when it crash, before the program finish the process, crash, core dump means whatever at that time in the memory, I save it to a file. That's why core dump. Core means the core memory, I dump it to a file. What is the use? It's like crime scene investigation, right? You go to a crime scene and see before things goes wrong, what happened? Is it someone try to start a fire, or is it somebody have a gun or whatever? What is there any dynamite or gunshot, whatever? You try to study the crime scene before every evidence is being gone. So the core dump is to dump the memory so you can actually see what happened before the program crash or something. So the finally is for that users that you actually can remember things before you finish. Okay, so the notes actually will cover that. For example, this one, if you do divide test 2-1, so it's totally okay. You will say use the else block, and then you will do finally. If you divide it by 0, you will catch by the 0 division error. If you do string of 2 divided by string of 1, at my example just now, I catch it, but in this example, I didn't catch it. So, and also it doesn't have a wildcard. It doesn't have to accept with anything. So it will crash. But before it crash, you execute the finally, then crash. Okay. So the finally block and the accept block is very good device to manage what happened if your program fail. But of course, in 1010E, you don't need to program some life critical system, right? But you know our recent MRT, whatever, right? There are things that will go wrong. So all this exception code is for handling those. That if something goes wrong, you cannot expect you will go to the error correction program, whatever, to stop the whole MRT or whatsoever. That's why the MRT stop in the middle if something go wrong, because it's the safest way to do it, right? If your MRT go on, it may even cause more damage or even lives. So there's all this life critical system. MRT is already like low risk. If you talk about airport, nuclear plant, the dam, the some more hospital, those are or chemical plants or you know we have a lot of industrial plant in the Jurong Island. All these need a lot of this error handling. Yeah. Anyone know this story? Cry wolf. What is cry wolf? The story is I assume you know the story lah. Cry wolf means there's no wolf, but you cry wolf, right? What do I want to say that? Because you see just now all the errors are by real happenings, but you can cry wolf. You can say there's no error, but I raise an error. Okay, you can suddenly just use raise an error or name error, then it's error, name error. So the Python will say, oh, you got an error, but why? Why do we need that? Of course, it's actually not very useful alone, but it's useful because you can use OOP to define your own error. Error exception itself is a class. You can define your own error. So as I said, maybe if you're doing an MRT system, you can define a signal error or electricity disconnection or no power error, whatever. So you define that error or that exception, and if something happened, you raise that yourself because the original system will not raise it for you. The original system is just raise error for its programming errors. But if you are doing a nuclear plant, suddenly your temperature raised to an unreasonable level, then you just suddenly raise an error and you try to do error handling. Okay, so you can create your own exceptions. Yeah, you can create your exception, and you can even give it a name as E and get some information. Actually, the exception is an object. You can actually even pass some information. Where, for example, if your nuclear plant is temperature rising, you can actually tell them which part temperature rise because the nuclear plant is so big, right? And you can actually pass some information to them to clarify the error. Okay, yeah. So, but we don't need you to know every error, but at least I want you to know most of the common error, like your type error, like your division by error, zero error, and so on. Okay. Remember we did our tic-tac-toe. Remember we said that we want the user to input from 1 to 9, right? That is a very wishful thinking. Your user is so experienced, you only input 1 to 9. What if the user doesn't input 1 to 9? The user input what? Then your whole program crash, right? So it's a good way, right? When you're losing, I just type what and then everybody lose. The game discontinue, right? So how do we make sure the user input the right thing? The original line of code is like this, right? You want to input the position. And in the input, you want to convert the user input to an integer. And when your user does not input digits, when he want to ruin the game, then it crash lah. How? Of course, one thing is we can do a lot of if then else. After you get in the input, you should first check the type and whatsoever. But why do we want exception is because if you want to put this if then else code into your code, it's very interrupting. Your code, your flow of your code is suddenly I have a big 10 lines of code and checking this error. So your thought of code and you make your code very unreadable. So instead of that, we do exceptions. We do this. And also the chances are you can do all you can to try to imagine what your user can be naughty to go through. But there will always be unexpected situation. Then how? We do this. I use a try block. In the try block, I do a break. And I trap it into the true forever while. What does that mean? That means if I can successfully convert the input into a position integer, I will break through the try block. Remember Dr. String? Anyone watch Dr. String movie? No? What are you doing in your youth? Dr. String movie, how did he beat the last guy? They trap him in what? Trap him in the time stone, right? He come to trap him in the time stone because the guy is too powerful and he got killed instantly, but he have this loop until the guy said that he is willing to retreat or whatever, then he keep trapping him. The child, sorry, spoiler, okay? But it's the same. Unless you give me an input that is suitable for me to convert it into integer, I let you go. Otherwise, please forever keep in my while loop. I will let you to play forever, okay? So this is how you trap the user until he gives you an integer. But of course, if you just say wrong, it's a bit irresponsible. So you should actually say maybe my except is this type error. I tell the user you input the wrong value or wrong type, whatever. The other error checking mechanism is called assertion. Error is when something goes wrong, you know. But sometimes in our program, we want to assert something. What is assert? Assert means we want to assume something is okay. For example, in tic-tac-toe, even the user input a number, it can be 100, 1,000, it's still not within 1 to 9. A lot of situations you want to assume. For example, if you want to implement a sorting function, you want to assume your user is inputting an array. When you are actually writing a function to check if a number is prime, you assume your user input a number, an integer, not a floating point, whatever. So you want to assume something before your program continue. So, for example, if you are searching, I don't know anyone do the list searching, you want to assume your index is within your list range. So in Python, you can put an assertion. What does that mean? Here. I can say assert 0 less than position less than 10. What does that mean? That means when I execute that line, I will check if the condition is true. If it's true, nothing happened. Go on. But if it's not, you will raise an assertion error. Okay? So assertion is like a bouncer. You know, the disco, whatever, bar bouncer. You assert if your age is larger than or equal to 18. If it's yes, just go through as normal. The bouncer is like immiscible. But if it's not, you will just raise an error and let you go. So it's assertion. Okay? But of course, you should be actually making more detailed error handling, except using for the while except. The while except is the last one, which without any condition. So if you want the assertion, that means when you violate the assertion, you know that the user actually inputs a number not in the range, then you tell the user put in the range lah. Because otherwise the user don't know why he's wrong. And why use exception? I think I mentioned a bit because all this reason is like an emergency exit. What is the good thing about emergency exit is it's more natural. You don't use it normally. And it's more extensible because you can do even inheritance or OP and are more flexible because you can even have multi-layer of exceptions. You can inside a try block, another try block, another try block, and you can catch exception in different layers. Okay. Anyone watch the Japanese anime, the Attack on Titans? Remember they have different layers, right? The layer of wars is a bit like that. Depends on emergency, how much war or how much thing you want to do. Okay, so they're exactly the same thing. And don't do this. Oh, my whole cook, sorry. Even my comment is wrong. What I try to say that is, some people will abuse exception. Why? I put my whole cook in the exception, and if something wrong, I pass. Okay? That means in anything wrong, you just patch it with an exception. Okay, so why is it not good? Because your program will just finish without telling you anything. Which I usually will refer to the human pain system. I know that pain is not good, right? But the pain on human sensation system is helping you to escape from danger. You touch something hot, you will retract, right? Because it's pain. You step on something sharp, you just extract because you know something is going to cut you, right? There's some people in this world is not so lucky they actually don't have the pain system or their nerve has some problem. What happened? Maybe they are touching something burning, they just suddenly smell something grilling stick, smell nice, but actually they're burning their hand. Some really is like that, but we pity those people. But some people in this world really don't have that type of system. It's very dangerous. Okay, and that's why the pain system is not an error system. It's good for your health. Of course, too much is not good lah. Okay, but then it's good for your program. You know where does it goes wrong. How do you handle it? So use it. Don't use it in an abusive term. Everything, because I know that there's one thing why we know some of you use ChatGPT is because ChatGPT, I don't know why it likes to use exception if then else statement. Even a simple if then else, they use exception. I don't know why. Yeah. So, okay. So the meme is if you know exceptions, yeah, there's something like that. Okay. So anyone knows this? I don't know. There's a lot of memes, right? This one is trying people play around with the words. Because she fell in love with an electrician, she feels shocked. Because she fell in love with a crane operator and she got let down. Okay, so it's playing with the words. Because she fell in love with a programmer and she became an exception. Why? Because people think programmers don't have girlfriend. The old meme, sorry, it was sue me for sexist, okay? Yeah, okay, so that's it. There's for exceptions, but use it wisely and please do not abuse it, okay? Yeah, it is a popular memes. You don't have to copy it from me, okay? It's recorded also. Thank you. Any more things from, okay, no more response. Thank you, and we'll try to finish our marking as soon as possible.